Hi everyone. In this video, we're gonna go over midterm 2 for the course Math 101 from 2024. It was on March 15. 3 questions, 45 minutes timeline, and like always, no calculator, nothing else, just everything from memorization, no formula sheet. So let's begin with the first problem. In this problem, we are asked to take this definite integral, which is an improper integral from 1 to infinity. So the reason it's improper is only this upper bound is infinity. The other reason that a one integral might be improper is what you have inside of that. It has a vertical asymptote. It has a point that it is not defined. So for example, here, the only point that it might not be defined is when the denominator of that is 0. The denominator here is, okay, let's just rewrite that. Instead of x multiplied by e to the power of negative 2x, we can write that as x over e to the power of 2x. This would be undefined if the denominator is 0. And you know that exponential graph or e to any power is never 0, and it's actually always a positive number. But if you remember the exponential graph, you see it's always above the x-axis. So this function, this integrand, basically does not have any vertical asymptote. So the only reason or concerning part is the upper bound, which is infinity. But regardless of the bound, we need to take the integral, or I can say antiderivative of this. So let's just focus on that for now, regardless of the bounds. So the antiderivative or integral of x e to the power of negative 2x dx. So in integrals, one of the challenging steps might be deciding what method to use. And the problem is, again, there is no specific rule to decide which one to go. So my procedure is always going through the easiest methods, for example, like U substitution, trig substitutions, and see if it works or not. The first method is U substitution, and if I want to use U substitution, I would say, okay, this is the U part. But if I just use that as U, the du would be basically negative 2 dx, which I have dx, but I also have this x, which makes the U substitution not a perfect method here. Obviously, the trig substitution doesn't work. There is no fractions here, so we don't have a partial fraction, and the other methods are not very practical. So we are kind of left with integration by parts. And in integration by parts, let me just write the formula here. We are taking the integral of u times dv, which it would be u times v minus the integral of v times du. So the first step would be deciding which part of this original integral is u and which part is dv. So to decide that, if you have no clue where to start, I would go with this mnemonic, which is ILATE, or ILATE, easier to memorize. I stands for inverse of trig functions, sorry, like arc sine, arc cosine, arc tan. L stands for logarithmic function. A stands for algebraic function. T stands for trig functions. E stands for exponential functions. So what we have here is we have 1x here and we have e to the power of negative 2x. So basically x is algebraic type and e to the power of negative 2x is clearly exponential function. So we have a and e from this mnemonic, a and e. Because a came earlier in this ILATE, so a would be our u. So basically it helps us to decide which part is u. And algebraic would be our u, and the rest of that, which means including the dx, would be our dv. So if we go with this one, and what do we need for the integration by part? We need u, which we know that. We need v, so we need to evaluate that, and also we need du, later on, which is kind of coming from this u. So let's just write it down. So u is equal to x. So from here, we can conclude that du is basically the derivative of that, which is dx, 1 dx. And dv is equal to e to the power of negative 2x dx. And v would be, basically, we are undoing the derivative. We are taking the integral of these. And the integral of that would be e to the power of negative 2x over negative 2. If you wonder how you can take this integral, you can write it down completely and it would be a simple u substitution. And now it would be the v, and now we can simply rewrite this formula. So we have integral of u dv, which is our original integral. So I just write it down again. X e to the power of negative 2x dx is equal to uv, which is this times this part, which would be x multiplied by e to the power of negative 2x over negative 2 minus integral of the du. Here we have v and here we have the du, which would be e to the power of negative 2x over negative 2 times du, which is simply dx. Now, instead of taking this a little bit complex integral, we are kind of just dealing with this simpler integral. So let's just take this integral. So here I can take out the negative 2, or let me just first write this separately, just this part. Do it here. So integral of e to the power of negative 2x over negative 2 dx. I can take out the negative 2. It would be, because it's in the denominator, it would be negative 1 over 2 integral of e to the power of negative 2x x, which actually we know already the integral of that. We had the same problem here. And the integral of that would be e to the power of negative 2x over negative 2. So overall, it would be just this negative and this negative, they kind of cancel each other, the signs, and these 2 and these 2 makes it 4 in the denominator. So it would be e to the power of negative 2x over 4. Now I can substitute this instead of, I can write that instead of that integral. So overall, my original integral would be x times e to the power of negative 2x over negative 2 minus this integral, which we already evaluated, that e to the power of negative 2x over 4. Now that we have the antiderivative, we can simply plug in the upper bound and the lower bound. Just make sure, if you want to write this properly, you should not plug in the upper bound as infinity, because infinity is not a value. You cannot plug that in any equation. So what we do instead, we just give it a letter, like a parameter, like for example t, and the lower bound would be as it was. It's just simply 1. And to indicate that t is a infinity, basically, we simply sorry about this, we simply need to take the limit of that as t goes to infinity. So instead of writing infinity as an upper bound, we put a parameter like a, b, c, or whatever you like, and you take the limit as that variable is going to, if it's infinity, it's infinity. If it was negative infinity, it would be negative infinity, or maybe other points that makes the function, the integral, improper. So again, regardless of these, we simply need to plug in these t and this 1. So I just write the limit here, limit as t goes to infinity of, okay, first we plug in the upper bound, would be t e to the power of negative 2t over negative 2 minus e to the power of negative 2t over 4. This is the upper bound, like round bracket, minus the lower bound, which is 1 e to the power of negative 2 times 1 of negative 2 over negative 2 minus e to the power of negative 2 over 4. Now, instead of t, we know that t is going to infinity. Let's see what happens to the parts that are kind of relying on t, which is this part and this part. When t goes to infinity, let's see what happens to this part. We have e to the power of negative 2 infinity, or basically 2 infinity is basically same as infinity. So e to the power of that would be e. Let's analyze that separately here. E to the power of negative 2 infinity is basically e to the power of negative infinity, which is, what does that negative do? It's basically mean reciprocal. It's 1 over e to the power of infinity. And you know, e is a number, e is a constant, like about 2.7-ish, and you are raising that to the power of infinity. So this denominator would be a very, very big denominator. And when you are dividing 1 divided by very, very huge denominator, the answer would be infinitely small, which we can call that 0. So basically this part, e to the power of negative infinity, is basically 0. Let's see what happens to this part. In this part, we have very similar situation, just we have also this t here, which is making that a little bit more complicated. So let me just analyze this part separately here. Let me just change the color. We just analyze that separately here. So we have t times e to the power of negative 2t. When t goes to infinity, we have basically infinity multiplied by e to the negative infinity, which, as we discussed, it is basically 0. But we know it's not exactly 0. It's a very, very small number, and the other one is infinity. Infinity times a very, very small number. What is the multiplication? Here, if I want to do it a very shortcut way, it would be, because this 0 is coming from exponential function, that is a stronger 0. That's basically overpowering this infinity. Because this infinity is only coming from a very linear function. It's coming from a polynomial. It's not that strong. So we can say that this multiplication is kind of overpowered by this 0. It's trumped by that 0. The answer would be 0. Or if you want to do it a little more proper way and explain it clearly, you can use L'Hopital. Whenever you have infinity times 0, you can use L'Hopital. So to do L'Hopital rule, if you remember that, you need to have a fraction. You need to have either infinity over infinity or 0 over 0. So let's do that. So instead of infinity times 0, what I can do, I can move this e to the power of negative 2t to the denominator. So basically it would be t times 1 over e to the power of 2t. Instead of e to the negative 2t, I just bring it to the denominator and it would have a positive power, which I can write it as t over e to the power of 2t. Now when I plug in infinity, I would get infinity over infinity, which is perfect in the use case of L'Hopital. So instead of taking this limit as t goes to infinity, we take the limit as kind of the derivative of them is going to infinity. Let me just write it down, it's more clear. So what I do, I take the derivative of the top and the bottom separately. Make sure that you don't apply quotient rule. We just take the derivative of the top part, t, which is just 1, and the derivative of this one separately in the denominator. It is e to the power of 2t times the derivative of the power, which is just 2 because of the chain rule. And now t goes to infinity. And what we get is 1 over very, very huge number, which is basically, again, 0. Again, this was the shortcut. This is a proper way of thinking about that, but both gives you the same answer. So what we get here is 0 from this part, 0 from this part. So basically, the upper bound is 0 when we plug that in. So what we are left with is just this part. So I just write that 0 because of this part, minus bracket, this 1 we don't have to write that, e to the negative 2 over negative 2 minus e to the negative 2 over 4. So this would be the final answer. Let's just clear that a little bit. So it would be, so this 0 doesn't matter. we just need to multiply this negative by the bracket. So what we get is e to the power of negative 2 over 2. This negative is basically cancelled with this. And it is plus e to the negative 2 over 4. So we can write that as the common denominator is 4. The numerator would be 2e to the negative 2 plus e to the negative 2. Overall, it gives us 3e to the negative 2 over. This would be the final answer, and because we got a specific number, a specific answer, it is basically converging to that. So it's not diverging, so it converges, and if it converges, compute the value, which we found the value. Value is this. If we got infinity, negative infinity, or D and E, kind of we couldn't say what it is, it means it is diverging. I hope it was clear what we did. If you had any question, feel free to let me know in the comments. In this problem, we are given a function f, which kind of it's an anonymous function, but what we know is f prime is continuous, and the integral of f from 0 to x would be f of x, the capital F of x. And we have some information about the value of the function f at 1, the integral of f from 0 to 1, and the integral of capital F, which is integral of, again, f from 0 to x, from 0 to 1, it's kind of a bunch of information about the function f. And here we are asked to evaluate the f prime of, the integral of f prime of x squared. Again, if we for now skip all of this information and just focus on this part, let's see how we can take this integral. So we have the integral of from 0 to 1 f prime of x times x squared dx. Here we have two functions, f prime of x and x squared, and these two functions are kind of, maybe f prime of x is also a polynomial like x squared. It's an algebraic function maybe, but it's totally unknown. It's anonymous. So we can say, okay, this is totally different function from these, totally different kind of nature. Maybe that's a logarithmic function, whatever that is. But the best way here to take this integral is just assuming that they are different and using integration by parts. In integration by part, you need to have, let me just write the formula again. So we have the integral of u times dv is equal to u times v minus the integral of v times du. So here we need to have a u and dv. So I can say this is my u, this is the rest is my dv. But the problem with this is later in integration by part, whichever part you choose to be your u, you need to take the derivative of that, you evaluate du, and dv, you need to take the integral of that to evaluate what v is. But if u is f prime, the du would be f double prime, which totally we don't have any information about f double prime here in this kind of background story. So it's better to use f prime as our dv. So when you take the integral, that prime somehow kind of disappears. So it's better to just say that this is u, and this part with this part together are our dv. Let me just write it separately. U is equal to x squared, and dv is equal to f prime of x dx. U is equal to x squared, so du would be the derivative of that, which is 2x dx, and dv is f prime of x dx, which the v would be integral of that. So basically this is already the derivative. We are doing the antiderivative of that, which would be back in kind of as f of x. So now we have the du, v, and everything we need for this integration by part formula. So I can write the integration by part formula as this: the integral from 0 to 1 of f prime of x squared dx is equal to uv. This multiplies by this one, which is x squared times f of x minus the integral of v du. This integral is also 0 to 1, but let me for now totally ignore the bounds. So just take the antiderivative, and later on we focus on plugging the upper bound and the lower bound. So it's integral of v du, which is f of x, and du, which is 2x dx. This part is already integrated, so it's okay. And now we need to deal with this integral, which actually looks a little bit better integral, because before, in the previous step, we were supposed to deal with x squared. Now we are dealing with 2x, or kind of just x, because the 2 is constant, you can take it out. So it seems it's a little bit of improvement. So now let's focus on this integral, just only this part. So I can write the integral of f of x times 2x dx. Let me just take out the 2, or kind of I can just keep it inside. I mean, it really doesn't matter. It seems, again, very similar structure as this one, so I can apply integration by parts again. So to do that, what I need to do is decide which part is u and which part is dv. If I just choose this part to be u and this part to be dv, when I take the derivative of that, it becomes u prime du, and it becomes f prime of x, the du. And if I do that, I will go back to this stage again. I would get f prime, and this one would be x squared, the v would be x squared. I would go back to the previous step. So usually, if you are supposed to do multiple times integration by part multiple times, usually you don't switch u and dv. I don't say it's a very general rule, but I would say more than 90% of the cases you don't switch them unless there is a specific trick to that specific integral. So if I started with taking the integral of f prime, I kind of keep doing that. So I would go with, this is my u, and these two parts would be my dv. So again, I write it separately here. Let me write it with blue. So u is equal to 2x, and f of x would be my dv. dv is f of x dx. So I simply take the derivative of the first one, du would be just 2 dx, and here v would be the integral of f of x dx, which we don't know what it is, so I just write it as integral of, actually we know what it is, actually it's written here. The integral of that would be the capital F of x, basically. Now that we know the integral of that, it's basically, it seems everything's working. Now I write the integral. The integral of f of x times 2x dx is uv, this multiplied by this one, which is 2x capital F of x, minus integral of v du, which is f of x times 2 dx. Let me write everything kind of together. So the original function, which kind of we started with, is here. So I'll just write that here. Integral of f prime of x times x squared dx is equal to this part, x squared times f of x, minus this integral. And instead of that integral, we have this part. So I just rewrite that minus. So because it is a negative sign, I make sure that I write everything in a bracket. It is 2x f of x minus the integral of capital F of x times 2 dx. So this would be basically the final answer. And then next stage would be, the step would be taking the integral of these, which is kind of, we cannot do anything about this one. No integration by part, nothing, because it basically has only one part. And if you just choose this as a u, you are basically going back to the previous steps here, which is not helpful. So we need to basically know this integral. And let's see if the information provided to us, the problem statement here, is helpful or not. So now let's put the bounds back. So the bounds were 0 to 1. So everything here are from 0 to 1. So the first part would be from 0 to 1. This part would be from 0 to 1. And this part is an integral still, so it's from 0 to 1. Now let's see what information we have and what information we need. First, let's just plug in the values. Let's plug in the upper bound here. So this 1 goes for all the x's here. So it would be 1 squared f of 1 minus 0 squared times f of 0. So this is the first part, minus. We have a big bracket. We plug in 1. It is 2 times 1 times capital F of 1 minus 2 times 0 times capital F of 0. I don't need a bracket here. Okay. This part minus this integral, which let me take out these two to the front here. So it's minus 2 integral from 0 to 1 capital F of x dx. Okay. Let's see what we have. This part is entirely 0. This part is entirely 0. And that's it. So what we need is f of 1. Let's see if that information is provided. Yes, f of 1 is 2. So I can simply plug in 2 here. What else I need? I need f of 1, the capital F of 1. The capital F of 1 is not provided here, but let's see what that is. The capital F of 1 is this function when I plug in 1 for x. So capital F of 1 is basically this integral from 0 to x, which x is 1 in this case, of f of t dt. And it basically is given to us here. The integral of, sorry, my bad. It's given to us here. The integral of f from 0 to 1. Perfect. So it's basically 3. So leave it here. This part would be simply 3. And the last part is integral of capital F from 0 to 1, which is directly given to us, which is just 4. It's 4. So let's just put all of them together. So we have 1 times 2, just 2. This is 0, so we have just 2. Excuse me, minus. We have these 3 and these 2 and 1. Overall, it would be just 2 times 3, which is 6. Again, minus 0, which I just write, it doesn't matter. And okay, I forgot this big bracket, minus this part, which is 2 times 4. So overall, it would be 2 minus 6 minus 8, which is 2 minus negative 2, for overall 2 plus 2, which is 4. So this would be the final answer to that integral, which was, again, for an anonymous function. Because we were provided with some information about that function and the derivative of that, we were able to complete that integral, this f prime of x squared. I hope it was clear what we did. We basically did integration by part twice, but if there was any question, feel free to reach out to me and ask your question. In this problem, we want to find the volume of a solid, which is kind of described here. So let's go over that description and try to kind of imagine how that looks like. So they said that it has a base on the xy plane, which is it's a region between the x-axis. So let me just have the xy plane. Between the x-axis, so between these axes, and the curve y equal to sine of pi x squared. If we don't know what that looks like exactly, it's totally fine. We don't need to know that. So to just make sure that, okay, it's really not needed, I just randomly draw a function. So it's between the x-axis, so here, and randomly I just draw something like that. I'm pretty sure this is not this function, but it's not really not very important. Let me actually just move it a little bit up here. Okay. And now from 0 to 1, so this is 0, and let's say this is 1. And when they said when you slice it perpendicular to the x-axis, which means in this way, wherever you slice that, so you get, for example, you slice it at x equal to x naught, the altitude of that slice would be 12x naught. So this is the most important part to kind of try to imagine how it looks like. So basically this is what, this region is what we see from the top view. This is the top view of this solid. And wherever we slice, for example, we slice it this part, we get a rectangle, which, for example, this is x naught. The altitude of that is 12x naught. So for example, if x naught is, I don't know, 0.5, the altitude of that would be 12 times 0.5. And the cross section of that looks like a rectangle. So it looks like something like this from the side. Or if I want to kind of draw that more precisely, let me just sketch that side view or cross section view here. We have a rectangle like this. This altitude, which is basically, sorry, it's kind of translated to this side, is 12x naught. And the height of that would be basically this line, or basically the function value. Let me just write that f of x. So at any cross section, wherever you slice it, you get a rectangle, which this would be one side of the rectangle, this length, which is the function value, and the other side of that, or basically they call it altitude, is 12 times the x coordinate of that point. So I can just leave it this way, and this is f of x. Now we want to evaluate the volume of this solid. So basically we are stacking bunch of these layers on top of each other or beside each other to create this volume. So we need to take the integral of that summation of all of those layers. So we can say it's the integral of the area, and it is dx because we are stacking them along the x-axis. You can just memorize it this way. So the volume is integral of area. And it's very important to know you are integrating along the x-axis or y-axis, because if you assume that you are stacking them this way, which is also possible to do that, but because of this description, which they said we slice it perpendicular to x-axis, so it's easier to do that. But if you are slicing this perpendicular to y-axis, it would be dy. So let me just erase these ones. So now what I want to do is evaluate the integral of those areas. And the areas are basically the function, which we have it here, sine of pi x squared, which is f of x, multiplied by that altitude, which is 12x naught, or here I generally write it 12x. At any point, it would be 12x. And dx. And I'm evaluating these integrals from 0 to 1. There's a 0 and 1. But the most challenging part of this problem is recognizing how it looks like, the problem, kind of this three-dimensional shape, how that looks like. And now that you know that the cross-sectional is a rectangle, you have just the length and the width of that, or kind of the height and the width of that to get the area. Now we simply need to evaluate this integral. To take this integral, one of the easiest ways would be the u substitution. Because here we have x squared, which when you take a derivative of that, you get 2x dx. And we have x dx here. So it's kind of perfect format for u substitution. But make sure that if there was no 2 here, the u substitution would not be very helpful. And here we need integration by parts. So if I just use this part as u, so let me just write that here, u is equal to pi x squared, du would be 2 pi x dx, and from here I can isolate dx, which is du over 2 pi x. Now I can rewrite this integral. Just because I'm changing the variable into du and the dx would become du, I don't put the bounds here anymore. Or if I want to write the bounds again, I need to update the bounds. So I can leave it blank for now. It would be 12x, I just write it here. And instead of sine of pi x squared, I have sine of u. And instead of dx, I have du over 2 pi x, which it was a perfect substitution because these x and these x, they cancel each other. Write it simpler, okay. And these 2 and these 12 also cancel each other, and we have 6 here. So now I have 6 there, I have pi here, both of them are constant, I can take them out. I can have 6 over pi integral of sine of u. And taking the integral of sine of u, the integral would be negative cos of u. So the integral would be 6 over pi negative cos of u. Make sure that I cannot just use 0 and 1 here because these 0 and 1 are for x value or x variable. So what I need to do, I need to undo the substitution. I know that u is pi x squared, so I simply write 6 over pi negative cosine of pi x squared. And now, because everything is in terms of x, I just simply write it from 0 to 1. First plug in the upper bound, we get 6 over pi negative cosine of pi times 1 squared. So this is the upper bound. Let me move these a little bit to the left. Minus when I plug in the lower bound, which is 0, which is negative cosine of pi times 0 squared. So here we have cosine of 0. Cosine of 0 is basically just 1. And here we have cosine of pi, which is negative 1. We need to memorize them. So now we have 6 over pi times, there's a negative 1, which makes it positive 1, minus negative 1, which is basically plus 1. So now overall we have 2 here and times 6 over pi, which is 12 over. This would be the final answer, which is the volume of this solid. And in case you are interested to know what are the new bounds here, if you wanted to update the bounds, these bounds are for x variable. And now you want to find the bounds for u variable. So if you see dx, it's an x variable. If you see du, it should be u variable. So how we should convert x to u? Through the substitution that we had here. So we simply plug in the 1 into this conversion. We get pi times 1 squared, which is pi. So the upper bound would be pi. And if you plug in the lower bound here, you get 0 still. So it's basically 0 to pi, or I can just transfer that here, 0 to pi. And at this point, also I could plug in 0 and pi right away. So I had two options, either the updating the bounds to the new bounds in terms of u, or bringing back everything in terms of x and plugging the original bounds. But at the end, the final answer is same, 12 over pi. I hope it was clear and understandable. If you had any question, any concern, please let me know.